Sometimes a linear map from one vector space to another sets up a perfect correspondence between all the vectors in the first space and all the vectors in the second space. When that happens, we call the linear map of vector space isomorphism, and we say that the two spaces are isomorphic. Let's look at that more closely. Now there's a couple different ways to say this. One way is, let's suppose that V and W are vector spaces of the same dimension. Now, for some linear transformations, T from V to W. Oh, I wanted to fix a basis. Let's say these are vector spaces of the same dimension, and let's let B be a basis of V. So let's say the dimension is n. B has n elements in it. For some linear transformations T from V to W, the set T of V1 through T of Vn might be a basis. Of W. For other linear transformations it might not be. There's no rule about linear transformations that says that when you apply the linear transformation to all elements of a basis of the first space that you definitely get a basis of the second space. So no rule says that a basis for V must map to a basis for W. So for example, let's let V3 be polynomials of degree less than or equal to 3. And let's define T1 from V3 to V3 by a polynomial P of x gets mapped to x times the derivative of P of x. Then T1 maps the basis 1x x squared x cubed to, let's see, 1 gets mapped to derivative of 1 is 0 times x is 0. X gets mapped to derivative of x is 1 times x, which is x. X squared gets mapped to derivative of x squared is 2x times x. 2x squared. And x cubed gets mapped to x times derivative of that, which is 3x squared. It gets mapped to 3x cubed. And this is not a basis because it's got 0 in it. You never have a 0 as a basis element. 0 can't belong to a basis. So therefore 0, x, 2x squared 3x cubed is not a basis of V3. Now let's look at a similar map. Let's define T2 from V3 to V3 by saying P of x gets mapped to the derivative of x P of x. Then let's say where this maps the basis. T2 maps the basis 1x x squared x cubed to one gets mapped to, so multiply it by x and then take the derivative. Derivative of x is 1. X gets mapped to the derivative of x times x, which is x squared. Derivative is 2x. X squared gets mapped to the derivative of x times x squared, which is x cubed. Its derivative is 3x squared. And x cubed gets mapped to the derivative of x times x cubed, which is x to the fourth, which has derivative 4x cubed. Now 1, 2x, 3x squared, 4x cubed is a basis of V3. So there's something different about these two maps. In general, if T from V to W maps every basis of V to a basis of W, then we call it bijective. Or an isomorphism. And then we say that V and W are isomorphic. And this is usually written V equal signs with a squiggly line on top, W. V is isomorphic to W. So T is bijective or an isomorphism if it is injective and surjective. That's where bijective comes from. The two active adjectives, it's bijective. And the coordinate version of this so again, if we fix bases B and C of V and W, then the transformation T is left multiplication by some matrix. Let's let A be the matrix of T with respect to the bases B and C. Then V is isomorphic to W. In other words, T is an isomorphism if A is invertible, if and only if A is invertible. A fact which is so important, I think I'll call it a theorem, is that every n-dimensional real vector space is isomorphic to Rn. And thus all n-dimensional real vector spaces are isomorphic to each other. The proof is, let's let B be a basis of the vector space V. Then the map that sends the first basis element to a column vector of 1 and all zeros, and the second basis element to a column vector of 0, 1 and all zeros, etc. Vn gets mapped to a column vector of all zeros and a 1. Is isomorphism. That is, we're sending and we've been using this fact all along. In other words, we map each element V of the vector space V to its coordinate vector. Now we're basically saying that all n-dimensional real vector spaces are alike. Isomorphism is Greek. I'm going to say roughly because I don't really speak Greek. For same form. Iso means same and morph means form. Same form. Now if V is isomorphic to W, then every equation in V corresponds to a very similar equation in W. So for example, let's let V2 be polynomials of degree less than or equal to 2. Let's let W be upper triangular two times two matrices. Then, so this is a real vector space of degree of dimension 3. This is a real vector space of dimension 3. So V2 is all of the elements of the form A plus BX plus CX squared, where A, B, and C are real. W is all the matrices of the form A, B, 0, C, where A, B, and C are real. These are both three-dimensional real vector spaces, so these should be isomorphic to R3, which consists of all vectors A, B, C, where A, B, C are real. And when I say every equation in one of these spaces corresponds to a very similar equation in the others, in V2 we have 5 minus x squared plus 3 minus 2x plus 4x squared. Let me move this over so I have more room. So 5 minus x squared plus 3 minus 2x plus 4x squared equals 8 minus 2x plus 3x squared. In W, 5, 0, 0, negative 1 plus 3, negative 2, 0, 4 equals 8, negative 2, 0, 3. And then in R3, 5, 0, negative 1 plus 3, negative 2, 4 equals 8, negative 2, 3. So, in some sense, these are three different equations. In another sense, all we're doing is adding coefficients that are in the same positions in each object, whether the object is a polynomial or a matrix or a vector. So these equations correspond. It's really exactly the same thing. 5 plus 3 equals 8, 0 plus negative 2 equals negative 2, and negative 1 plus 4 equals 3. Just written three different ways. And the corresponding bases are 1x x squared for V2, W, they're 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, and in R3, they're 1, 0, 0, 0, 1, 0, 0, 0, 1. So when we do computations in any one of these three spaces, we could just do the same computation in another one of the spaces if we want to. It's like saying the same sentence in three different languages. The end.